maybe how I solve them. That's what I am trying to discuss in the first session. Okay, so let's begin. So artificial neural networks, yeah, you might have heard this introduction many times, maybe in the previous session, maybe you already know what are these ANNs. But for getting an idea like how this maps to our hardware implementation, let me quickly go through the background once again. Okay. So in deep learning, there are many ways of implementing it. So deep learning is something which lies below machine learning. And in deep learning, we usually use so-called artificial neural networks to implement it. So that implementation can be in purely software-based implementation or hardware implementation or some kind of hardware software co-design approach, whatever we like. But essentially what we are trying to do is we are trying to mimic the brain of living organisms, specifically the brain of humans. That's what we are trying to recreate. So basically we say like ANN, it is like a computing system inspired by the biological neural networks that constitute animal brains. Now, if you see the history of engineering, we got inspiration many times from nature, and we have tried to implement it. If you like humans, they always wanted to fly, so they initially looked at the nature, like how birds are flying there, and we tried to replicate it exact same way. And many people, they even lost their life trying to fly like birds, right? So here also similar thing. We are not trying to exactly replicate a brain. To do it, first of all, we might know all the details about brain, and it is told like we know more about the surface of the moon rather than our own brain. Okay, so we still don't know many things. That is one thing. But some basic operations, how it is happening in the brain, we have some idea. So we are not trying to exactly replicate it to build an artificial neural network. We are more or less getting inspired from that, how it is working. And we are trying to more or less somehow mimic it. We are not trying to So in this session, I am discussing this one, the feed-forward neural network, the traditional one. And this is also called a fully connected neural network. Because
Vipin,
I think my internet has a problem.
Yeah, so video you can switch it.
Okay.
So, yeah.
Okay. So this is also called a fully connected neural network because all the circles here, they are representing our neurons. And here basically they are arranged in layers, right? They are arranged in different hierarchy. And one neuron from a particular layer is connected with every neuron in the next layer. That's what we call as a fully connected one. And data goes from always from this first layer to second layer to third layer. So that's why we call it as a feed-forward network. So this is a fully connected feed-forward neural network. That's what I'm going to discuss today. But our brain is not like that. It is totally different. Okay? You might not see this kind of feed-forward happening there. But still, it can do many things. Okay. So we will first of all have a broad overview of this biological neuron, because basically we are getting inspired by this neuron, right? So basically, as you might be knowing, like you might have studied in biology also, our neuron, it basically has two main parts. It has some kind of body cell, which we call a soma also, and there is a long axon coming from that soma. And the body is connected with many, many other neurons, which are around it. So if you look at in the brain, one neuron might be connected to around 10,000 surrounding neurons, tens or hundreds of neurons, it will be connected. So when we say connected, Actually, they are not touching each other, where they sit very close, but they actually do not touch with each other. Okay, so the ending of one neuron, and you can say like the ending of the other neuron, there is a small gap between that. We usually call it as a synaptic cleft. And the entire structure, which is like, let me still use the term connected, but remember they are not touching each other. The entire junction, that's what we call as a synapse. So basically what happens is when the surrounding neurons, they want to communicate with this particular neuron, or when they want to connect with this particular neuron, what happens is from the end of the axon, which are called these axon terminals, some chemicals are actually released, like acetylcholine. Some chemicals are released from there. And those chemicals, they will get attached to the end of this body, which we call as the dendrites. So this is kind of lock and key kind of mechanism. So chemicals come from this end that will get attached here. So basically this guy, he will be like activating the neuron connected to that. But remember, it is not like one neuron is just connected to another neuron. One neuron is connected with many neurons. Okay, so how strong this connection is depends upon how many synaptic connection is there between these two neurons. The more number of connection, we'll say like the connection strength is more, because more amount of chemicals are released when one neuron becomes activated. Okay. We also have a concept like neurons which are connected together, wired together, they fire together. That is one way of learning also. Maybe, I don't know, in some other session you may learn, like the Hebbian learning. That is the basic concept. So neurons which have strong connection between them, when the first neuron fires, the probability that the second neuron that also fires, firing basically means he will get activated and he will release these chemicals. That probability is more. Okay. Now, as I said, yeah, so this guy, he connected with many other neurons. And what happens is when they fire, the chemicals are released. That will create some kind of voltage at the receiving neuron. And all the voltages from all the neurons which are connected with this particular neuron, they get kind of summed up at a place called this axon hillock. So they get added, and that voltage will be propagating through the axon. So that is what we call as the action potential. So that voltage will propagate through the axon, provided that voltage is above a certain threshold value. If the voltage is too low, nothing happens. If the voltage is above a threshold value, it will propagate through it. It will come to this terminal, and this neuron will be releasing chemicals, which might activate the next neuron. Basically, this is how a biological neuron works. So to build our artificial neural network, we just need this basic concept. So basically, neurons are connected with each other, that we know. And their connection strength varies. Not all neurons are connected with every other neuron with the same strength. In the biological neuron, that depends upon number of synaptic connection. So somehow we need to replicate in our artificial neuron also. Okay. We cannot have chemicals in our circuits. So somehow we need to replicate that concept there. Another idea from here is, yeah, each neuron, it somehow accumulates these voltages coming from his neighbors. So we need to have some kind of accumulation operation also, so that we can also accumulate the voltages. And only if that voltage is above a particular threshold value, he will fire, means he will release some chemical. So in our artificial neuron also, we need to somehow replicate that idea. Only when the voltage is above some threshold value, then only we should make our output high or low, however we are implementing. So only this much is enough from our artificial biological neuron to implement the artificial neuron. Okay, for the kind of neural net that we are designing. Remember, okay, we are aiming for this feed-forward neural net. For that, we need only this much from our artificial neuron. If you are implementing some other kind of neuron, network, like spiking neural network. We may have to know more details about biological neuron in order to implement it. Okay, so for the kind of neural net that we are designing, this much is enough, good enough. Okay, so let's try to implement those concepts in our artificial neuron, the neuron that we are going to design. So the first idea is each neuron, it is connected with many other neurons. Saying something. Okay. Each neuron is connected with many other neurons. Now, how can we implement it? So from a hardware perspective, for me, that is like I have a circuit, and that circuit is connected with many other circuits. Right? So quite straightforward. So I'll be just representing them like some wires here. So each wire here, it is representing like the connection between one neuron and his neighbors. So depending upon how many neighbors are there, I will have those many wires there. Maybe 100, 200, 1,000, whatever it is. So this X1, X2, X3, these are representing basically the input coming to this neuron. So from a circuit perspective, they are nothing but voltages. Okay. So they just represent some voltage. So the idea of the chemical, I am replacing it with the idea of this voltage. Now, okay, few things I'll discuss later. Okay, so these are the connection. Then we saw like these voltages, they are getting added at the axon hillock. So to implement that idea, again, very straightforward from the circuit perspective, I will just have a accumulator there who will add these voltages there. Now, another important idea from the biological neuron was not all connections are of same strength, right? We discussed. So the more number of synaptic connection, the more the strength is. So to bring that idea here, I am introducing the idea of so-called the weight. Okay, so these are some numbers which are basically representing how strong the connection is between this particular neuron and a particular neighbor. So practically when we implement these weights, they are nothing but some numbers which represent the strength of the connection. The more the weight value, the more the connection strength. Okay. Now, if I discuss about sign, okay, if you want to represent, okay, so then I just need to mention one more thing when we discuss about biological. So last time I said like when a neighbor fire, he releases some chemical and that may activate this guy. That is some kind of positive connection. Okay, there can be a negative connection also, which we call as inhibitive type of connection. So in the inhibitive kind, what happens is when a neighbor fires, that is actually preventing this neuron from firing. Okay, so to find out exactly whether he will fire, whether his output will be high or low, we will have to consider all the neighbors. Some of them will be giving this positive, some of them will be inhibitive. We need to add them up, and whether the result is again inhibitive or positive, we need to see. Based on that only it will fire. Okay, maybe that concept also we need to bring here, because our weights, they can be positive or negative. So to represent like it is inhibitive, I will use some negative numbers as weight. To represent like these inputs are encouraging this neuron to fire, I'll be using some positive values for the weight. So weights are nothing but numbers, but they can be positive or negative. And yeah, so basically what I will do, I will take each input from here. I will be multiplying it with the corresponding weight, and I will do a accumulate operation. So this is nothing but dot operation. No, so in many neural network packages, software implementation, as well as textbook, you will see like this operation is simply represented as a dot operation between X and W if you represent them as two vectors, because that is the case, right? You're just multiplying each one, summing them up, and you get the output. which is nothing but the dot product. Now, from the natural neuron, you know, like this sum, it should be above a certain threshold value. Okay. Only if that is above a certain threshold value, the natural neuron, it will release some chemical. So to bring that concept here, I have one more block here, which is called activation function. Some details we will see later on. So this output I am giving to this activation function. So in the simplest sense, this activation function can be a threshold logic when I implement it as a circuit. That means only if this voltage is above a particular value, I'll make my output high. If the value is below that threshold value, my output will remain low. Okay. So basically, this is the artificial neuron corresponding to this biological neuron. And our aim is basically to implement this neuron. So first I'm going to discuss how we will implement a single neuron. And later, by combining many neurons, we can build our entire network. If you want to ask something at this point, you can clarify. Nothing? Okay, fine. So this, yeah, as I mentioned before, we are going to discuss about feed-forward neural net. Again, terminologies you might be knowing here. We have neurons here, all the circles, we are just representing the neuron. The first set of neurons, okay, we call it as the first layer. We call it as the input layer. Last layer, we call it as the output layer, and everything in between, we call them as hidden layer. And we'll call a neural net as a deep neural net wherever you have more than one hidden layer. For example, this you can call it as a deep neural net because it has two hidden layers. Okay. So if there is only input layer, one hidden layer, and one output layer, we won't call it a deep neural network. We will simply call them as neural net. If there are more than two hidden, we can call them as deep neural net. And these arrangements, each column here, we will be referring them as layer. So this is input layer, two hidden layer, and an output layer. And here you can see a term dense here. Okay, we will call a layer as dense if it is fully connected. Okay. It is fully connected, I mentioned last time. So for example, here, every neuron in the dense layer 1 is connected with every neuron in the input layer. That's why we call it as a dense layer. Same for this one also, dense 2. Softmax, okay, maybe we'll discuss later. Okay, now the question is why we are looking at hardware artificial neural nets. So if you see, a lot of software packages are already available. Maybe you have used also. We have TensorFlow, which is quite popular. There are other packages also like Cafe, and TensorFlow is built on top of previously existing packages. Okay. Then there are a lot of Python-based implementation available for ANN. Now, why we are looking at hardware implementation of ANN? Okay. So the answer is typical answer to any hardware implementation. Okay. But the first one is very important. The main motivation here, at least for me, is due to the architectural similarity between ANN and hardware. If you look at the architecture of a neural net, you will see like it's highly parallel in nature. Okay. It's quite suitable for concurrent implementation because we have many neurons sitting in parallel. And hardware is inherently parallel in nature. Okay. So it's quite suitable for hardware implementation. That is one of the major reasons. That is one reason why even in software implementation nowadays, you will not execute your neural net on a CPU. You usually go for a GPU based implementation because GPU, although it is not like as parallel as a pure hardware implementation, It also gives more parallelism compared to a traditional CPU kind of thing. In GPU, you have hundreds of small but less powerful processors sitting in parallel, and maybe each processor can emulate a neuron, and they can work in parallel. So that will give you some performance improvement. But here I can have a specific implementation in hardware, whether it is using FPGA or whether it's using ASIC, whatever, where I can implement this entire network in parallel, and the performance will be much, much higher than a pure software-based implementation. That is my main motivation. Okay, architecture is quite matching, and because of that, the performance might be much higher compared to a software implementation. That's what is motivating us to look for hardware-based AML. Now here I haven't put design implementation challenges. I have written like consideration, but many of these considerations, they are challenges also. Okay, so hardware implementation, as you know, it is not as straightforward as software implementation. Many of the challenges which you encounter in any hardware implementation that exists here also, like your design time may be quite high compared to software implementation. Then debugging in hardware is more challenging. All things are still there. In addition to that, you need to consider a few things which are specific to an implementation. Okay, so that's what is discussing in this session. Okay. So first and foremost, the training part. So you might be knowing, right? Whenever you make a neural net, in most cases, okay, there are neural nets where you have like two kind of training. You might have that. There is supervised and unsupervised. The one I am discussing here, the feed-forward one, they are supervised neural nets. That means, first of all, they should be trained somehow. Only after training, they can be deployed. So in those kind of neural net, training on hardware is quite challenging. And in most cases, we will not do a training on pure hardware. Why? First of all, training in hardware, we need additional circuitry for doing this training operation. Okay, and that requires a lot of hardware. So if I implement the circuit for training also inside, say, my FPGA, the size of the network that I can implement inside an FPGA will be very, very limited. So because of that, I will not attempt to do training on pure hardware. That is one thing. Second one, the algorithms that are used for training, they are not hardware friendly. Again, the most popular algorithm, as you know, it is a backpropagation, which is like a gradient descent algorithm, which requires a derivative operation of the actuation function. Now, if you make a circuit to find the derivative and all in the hardware, again, that's going to consume, first of all, that's very difficult to implement. Second one, again, that is going to take a lot of hardware. So because of that, again, I will not attempt to do training on hardware. Another one, training is, again, in case of a supervised one, which is not using this reinforced kind of learning, you usually do training once. You train the network, and what is the purpose of the training? The purpose of training is to find the network parameter. Basically, what are the network parameter? The weight values that we discussed before. And there is one more parameter called the bias values. Okay, so we will have weights for each neuron, and there will be one bias per neuron, which I haven't shown, but usually every neuron will have a bias also. The whole purpose of training is to find the weights and biases so that the error of the network is minimized. That's what we are aiming for. And usually you'll have a set of data for doing this training. And the training usually happens only once. And once you do training, you get the weights and biases. That's it. After that, there is no need of the circuit which is used for training. That's a waste. Okay. You just need this weights and bias. So because of that, again, it might not make sense to implement the circuit for training in hardware. And lastly, for many applications, the time taken for training is not critical. That means you can do an offline training, okay? Maybe in software. I will do training in software. I will find these weights and biases, and I will use those weights and biases for my hardware implementation. Now, again, remember the main motivation for hardware implementation was performance. And here I am claiming that the training doesn't affect performance. Okay? And maybe I can take 4 hours, 10 hours, 1 week for training just to get the parameters, weights and bias values. Then I will use them directly to implement my hardware. Because how much time it took for training doesn't matter when I actually deploy my network. Okay. So that is what I am going to do. I am not going to do training in hardware. I will do a pre-train. Most cases, personally, I do it using TensorFlow. I extract the weights and biases from that software model, and I directly use those parameters for my hardware implementation. Yeah, it is one thing. Second thing, yeah, so last time when I drew that neural net, I showed that some wires are coming inside, wires are going outside. When you do a software implementation, like using some kind of Python package, most cases, you don't have to worry about what is the specific data type used for this net implementation. In most cases, the package will be using either 32-bit floating point number representation or 64-bit number representation. Okay. No need to worry. But when we come to hardware implementation, that is not the case. Okay. Because in hardware, that's an advantage also. When we go for hardware implementation, we can have precise bit width. I can specify any bit width from 1 to any number. In fact, you will see papers where there are hardware neurons implemented using single bit. Okay, the bit width is 1 for representing everything, weights, bias, connection, everything is just 1 bit. That's also possible. Now, if I use larger bit width, the advantage is the precision might be higher in my hardware implementation, but the price I am paying is again more number of resources. Okay. More number of resources, the impact is the number of neurons that I can implement inside an FPGA or ASIC is reduced because the number of resources that I have or the maximum chip size that I can have is limited. Okay. So this somehow we need to find out what is the best bit width for representing my number. If you use too small, error will be there, as I mentioned before, but the resource consumption will go lower and lower. Another impact is not only this error, the chances of overflow and underflow will come there. So that also we should be very careful, right? So if some overflow happens, large numbers will be represented like very small number, and if maybe underflow happens, small numbers might be represented as large number, which will totally mess up my network. So that we should be very careful. Another one is the number representation itself. Okay. So generally, the input to the neural nets are generally positive number. That could be some pixel values if you are doing some image processing or some sound samples, if you're using some audio processing or natural language processing. The inputs will be generally positive, but there are cases where inputs are negative also. Okay. The weights and biases, they can be positive or negative in almost every case. Why that is the case, I mentioned before, because sometimes the connections are inhibitive to represent it that I will need negative weights. And biases, okay, why bias is required, maybe you can read somewhere else. That is to give more flexibility to our neuron. That can be also positive or negative. So we cannot make any assumption about that. And in almost all cases, these will be numbers with some fractional part, some floating point part. Now, as I mentioned before, software implementation, if you check, they'll be almost always using 32-bit or 64-bit floating point representation. Now in hardware also I can do it. Okay. In hardware, actually, I have two choices. I can either go with the floating point itself, which may give more accuracy, or I have the choice of using fixed point representation. Now, advantage and disadvantage you might be already knowing. Using floating point, you can represent very, very large number. That is one advantage. But again, its hardware implementation is quite challenging, especially floating points. They are very suitable for multiplication. You can easily do that. But when you do addition and subtraction using floating point, that circuit has to be more complicated. So again, if you're using some FPGA tools, things like that, you cannot directly write it in your Verilog. It won't work. You will have to instantiate some specific IP cores, like the Cordic IP core, to implement this floating point operation, which are very resource intensive. So what we will do, we'll not go with floating point representation. We will go with fixed point representation, okay, which may give less precision, but the circuit complexity is greatly reduced if I go with fixed point. So again, the last point, it is not always true, but true in many cases. Usually when you feed an input to the neural net, you will normalize the input and you will feed it. That means the input will be represented between 0 to 1. As I mentioned, if it is always positive, you scale it between 0 to 1. Or if negative numbers are also required, we will scale it between -1 to 1. Okay, that's the kind of input going. So what happens is in many cases, you don't have to represent very large numbers. You have to represent very small numbers. But what we will prefer is better accuracy. So even when we are going with fixed point representation, this should be kept in mind. I'm using fixed point, but the number that I'm trying to represent is not very large. What I'm interested is representing that fractional part with better accuracy. Okay. So these things, I know, these slides, I made them for students also. That's why there is more discussion about fixed point representation, but you might be already knowing it. Okay. Okay, so I'm just giving an example here. For example, say we are going with 15-bit representation. If my data width is 15 bits, and in fixed point representation, you will have to basically specify how many bits you are going to use for representing the integer part of the number and how many bits you are going to use to represent the fractional part of the number. For example, if I am saying I'm using 10 bits for representing fractional part and 5 bits for representing integer part, and when I represent 15.84 in fixed point representation, this is how it will look like. Okay, so this is integer part, which is plus 15, and this is fractional part. It is not exactly 0.84. If you see, this part is actually 0.8398437. So some precision I lost, which is basically 1.9 into 10 to the power of -4%. Some error is introduced. So that will not immediately affect the quality of my output. But what is possible is, again, if I'm using it for representing my weight, as you know, basically I am accumulating it inside a unit. So if I have many weights coming, representing connection between many neurons, and if I multiply them with the input, and that when I add them together, I'll be basically accumulating this error. Okay. And beyond some certain level, it will start to affect the quality of the output. Otherwise, this is perfectly acceptable. Now, this is just showing, like, if you try to use only 10 bits representation instead of 15-bit representation, instead of 15.84, I'll be basically having 15.8125. I can represent only that much. Again, error increases, but I reduced 5 bits in my number representation. Remember, this number representation, this connection is going to every neuron. So there will be hundreds and thousands of buses with this particular bit width. So you reduce 5 bits per bus means the amount of resources that you are saving is enormous actually. Okay, that's quite high. But the additional error that you introduced is this much, 0.0275. So there should be some way, there are ways to find out which is the optimal number representation. And first of all, we should somehow find out what is the optimal number representation before going for a particular implementation, because that can make or break your design. Okay, and another choice that we usually have is again whether to go with signed magnitude representation for these numbers or 2's complement representation for this number. Again, both have their own advantage and disadvantage. What these things are, I guess you already know. Now, the signed magnitude representation, that is not very suitable for addition and subtraction, because inside the accumulator we'll have to do addition. Effectively, addition and subtraction, they are same, right? In 2's complement. So that operation we'll have to do. In that case, maybe 2's complementation is quite good. But using weights, we will have to do multiplication also. So in case of multiplication, 2's complement is not very efficient. So in multiplication, maybe signed magnitude is better. Better in a sense that takes less FPGA resources. Okay, the multiplier for normal multiplication is less complex compared to the multiplier using 2's complement multiplication, which is basically signed multiplication. So there, it might be better to use signed magnitude representation. Okay, so that's about number representation. Next one, this actuation.
Vipin, there is one question on the chat window.
Oh, okay, you can stop me and ask anytime. Can I train the neural network using GP and then use the train values on dedicated hardware? Yes, that's exactly what I said. Okay. You can run your TensorFlow model or PyCharm model on GPU, then you will save your model, right? After saving, there are APIs for extracting the parameters. You extract the parameter and use those parameters to implement the hardware. That's what I'm also doing. Okay. Is that okay, Taru?
Yes, sir.
Okay.
Thank you.
Okay, next one, this actuation.
Sir, I have a question on the data width considerations.
Yeah.
So,
don't call me sir at all. You just
yes. Yeah. So for the data width consideration, when we use bit width too small, there is a situation of getting a large error, right?
Yes.
In one of the sessions yesterday, like we were introduced to the binary neural network. So how would that perform better, or what is it significantly different there, which gives us a optimal solution?
In binary neural nets, you have only ones and zeros, right?
Yes, sir. Yeah.
Okay, so if you're implementing a binary neural net, fine, perfectly fine. This is more like a generic implementation. Yeah, I am not making any assumption about the numbers that we'll encounter. Okay, so let me say practically how it is done. So this is one place where software training gives us some advantage. So what I will do, I will do software training first, and after training, I'll be getting the parameters, right? What are the weights and biases I will get after software training?
Yes.
Now, looking at those parameters, I can directly find out what is the maximum width I need, which will be log 2 of the maximum parameter value. That's okay?
Okay.
Yeah, that is fine. So from there, I got it. Maximum parameter value. Another thing that I need to find for bit width is this input. how large the input numbers will be, because I will be multiplying the input with these weights and summing them up. Is that okay? Now,
Okay.
if the inputs are normalized, my life is very straightforward. I know input will be always between 0 to 1. So maybe I just, inputs are very small. Okay, very
Okay.
straightforward. And again, that is about the first neuron, because he is the one who is getting the input from the external one. Other neurons, they are getting it from the intermediate neurons, right? There, this activation function, they also play a role. And in many cases, the activation function values are also scaled between 0 to 1 or -1 to 1. Most cases 0 to 1. We'll discuss it, those who have heard it before. Like sigmoid, the values are between 0 to 1. Tangent also 0 to 1. So in that case also, I know intermediate values are also like that. And I know each neuron, how many inputs are there. So say 100.
Okay.
So based on this, I can find out what is the largest number that is going to come. I will take the worst case. I will say my input is 1. Every weight is the largest weight I got after training. Okay. How many inputs are going to a neuron? I know, because that's how we design the neural net. Say like 100. So in the worst case, this weight times this input gets accumulated 100 times. Right? So weights require n bit, input requires m bit. So multiplication, it will require n times m bit width. And if I am adding it 100 times, each addition may require one additional bit. We have the theory. I can find it out how many bits I need in the worst case. Is that okay?
Okay.
That's how
Yes.
I get the worst case. Now, I don't have to go with that also. I will show in the coding later. I can go with a smaller number also, but I need to put the so-called the saturation logic to counter this offer issue. So that logic will be checking, because internally I'll be using a large value. Output of my adder will be high. More number of bits will be there. That output I will check. I will check whether it is larger than the maximum value supported by this bit width. If that is the case, I will saturate it and send it. We'll see in the code. Actually, code I will show.
Sure, sir. So one more thing on the normalization,
Yes.
which we were talking about, mapping it between 0 and 1.
Yeah.
So is this a kind of pre-processing or the host?
Yeah.
Okay.
So using software training itself, before training itself, inputs will be normalized. Usually.
Okay.
If you see again in the TensorFlow code or anywhere, inputs will be normalized before training, and that's how the training will be done.
Okay. Thank you.
Okay. Whether you use the exact input or normalized input, that will not have any impact on these weights and biases actually, if you see, because all inputs are normal. They are all scaled by the same factor. So effectively it's same as directly using. Okay.
Yeah.
Now in hardware, okay, so you can do it, and later actual software implementation, when you test at that time, whether you use normalized input or whether you used not normalized input, proper output will come. But in case of hardware, the only thing is if I used everything normalized, then my input bit width will be also based on this assumption. Input is normalized. That means in hardware, I may require an additional block for normalizing it when I actually deploy it. If there are pixel values something, I will have to normalize it before feeding.
Okay. And the normalization that we say is different from the quantization.
Quantization, normalization is just to represent between 0 to 1.
It's a scaling.
Yes, the other one,
yeah.
Quantization, you are truncating, right?
Yeah.
That is what we call as the quantization. Yeah.
Okay.
After
so that
normalizing
is
it, I got like 0.3245345C, but I may represent just as 0.234. That is a quantization. First one is
Yeah,
like a
yeah.
normalization.
And quantization could go to the weights and biases as well,
Yes,
unlike
yes.
normalization. Yeah. Yes, sir. Yeah. Thank you.
Yes, quantizer, yeah, weights and biases, we won't normalize. No, there is no guarantee there will be between 0 to 1. No, can be any value. But yes, there will be some truncation because, yeah, I'm using fixed point representation.
Sure. Okay. Thank you.
The activation function, yeah, this is our last block in our actual neuron who gets fired, right? When the input crosses a certain threshold value. Now, initially, the first proposed neuron, that was like a pure threshold logic. That means if the value is greater than, say, some 5, output will be high, otherwise output will be low. And the performance was not that great. That's why performance was not so high, mainly because it was linear. So you cannot do a non-linear classification using those kind of activation. Those neurons were called perceptron. That was very interesting. Then later, more non-linear kind of activation functions were introduced. So very, very popular one is called the sigmoid activation function. This is the equation 1 by 1 plus e to the power of minus x. Now, practically, when you implement this, x will be the output of our accumulator. Right? You multiply it, you add things together, and whatever is coming out of that, that will be going as the input to the activation function. So the x here, everywhere that you see here, that is the output of our accumulator. Now, this is a nonlinear one, you can see, but the value will be always maximum value x can be infinity minus 0, 1. This can be 0. So it will be always between 0 to 1, guaranteed. So this is like normalized between 0 to 1. Okay. Now, why that is important? We quickly go back to the architecture because the previous question. So see, from our external world, input is coming. That I have control to normalize. So I can normalize and feed to this layer. Now, as far as this layer is concerned, his input is coming from here. Now, if I use sigmoid, good thing is the input to these guys, that is also guaranteed that will be always between 0 to 1. Okay. So it is more like, again, normalized. For this guy also, that is the case. So that's the advantage of using sigmoid as well as hyperbolic tangent. That's also the case. So sigmoid was very popular. Again, feed-forward networks, still sigmoid is very popular. But in recent years, this one, ReLU, is becoming more and more popular. Rectified linear union. Okay. So its equation is very straightforward. If the input to the activation function is negative, output will be 0. If the input to the activation function is some positive number, output will be same as the input. That's the case. So it is very attractive because it is very simple. Right? Not like this. You don't have to find any exponential and all. It is very straightforward. So software perspective also, this looks less computationally intensive because ultimately if you're using CPU, GPU, he will have to find this exponential to implement sigmoid. But here it is very straightforward. So software people are very happy. But as hardware people, for us also, this is very easy to implement. But again, the issue here is, yeah, I have no control on the output. No control in a sense, there is no guarantee that the output will be within 1. No guarantee. Because if the input is positive, after I do multiplication accumulation, I'm giving it to this guy. If that is a positive number, the output will be same as that input. So that can be large number. There's no guarantee that will be 1. So if you're using ReLU, remember to have some saturation logic to make sure the output does not go beyond the maximum value that can be represented using the bit width that we have chosen. So in case of ReLU, we will need it. But in case of sigmoid, we won't need it. Now, usually one question that comes back here is again, No, that I will say generally, sigmoid and tangent, they were introduced claiming that the previous simple threshold one that is linear, so it's not good for classification. But if you see, this one is linear, rectified linear unit. Name itself says it is linear. But it was found, like many applications, especially CNN, convolution neural network, image classification, ReLU performs much better than Sigmoid, although it is simple. So yeah, so linearity is fine here. But the advantage compared to our traditional threshold logic is, in traditional one, this is how output will look like, sorry, like this. Okay. Now here again, this is not good because there is a discontinuity here in the function at that threshold value. So what happens is when you're doing the training of the neural net, we'll have to find in the backpropagation derivative of the actuation function. Now, good thing about sigmoid is derivative of sigmoid is very straightforward. Okay. Sigmoid of ReLU is also very straightforward. Y equal to x differentiate, you will get 1, right? Derivative is 1. But in this case of threshold circuit, you cannot find a derivative here. There is a discontinuity in the function. That's why this is still not preferred. But ReLU is preferred, although it is linear in nature, especially for CNN. Now back to our hardware implementation. So as I mentioned before, if it is ReLU, no issue. You just have to add a saturation logic. Hardware implementation is very straightforward. Now sigmoid and tangent, if you go with the equation and try to implement it, you will see there are papers where they have done this actually, means there are digital circuits which actually implement this function. And in case of FPGAs, we have IP cores, again, coordinate IP, which can find the exponential. Once you get exponential, yeah, you have to do this one. Again, in case of division, you have to again use a coordinate IP to do the division. So I'm not saying it is impossible, but again, the amount of hardware required for doing it is very high. And we need to keep the amount of hardware less so that I can implement more number of neurons in the given chip. So we will not go with exact implementation of this function. Instead of that, what we'll do, standard technique, again, you might have seen like to implement sine wave or cosine wave inside digital circuit, how we do it. We just pre-calculate them. Again, for pre-calculating, I need to know what is the range for X. If I know what is the range for X, I can do a pre-calculation. And if the input is normalized, and if every neuron is using sigmoid, then I will know what is the range for X. What is the maximum value? Minimum value will be 0 for X. Not minimum, sorry. Minimum value need not be 0 because I have negative weights also. But input is normalized. That is between 0 to 1 or minus 1 to 1, I know. Weights and biases, I know. Based on that, I can find what will be the minimum X value, what is the maximum X value. And based on that, I will pre-calculate this value, 1 by 1 plus e to the power of minus X. And I will store those pre-calculated values in some memory, okay, which we basically call as the lookup table. And I'll be using this lookup table for generating these functions. I will not be directly calculating them. So what basically happens, the output from our accumulator, that I will be giving as the input to this ROM. Basically, it will be going as the address to the ROM. And I have the pre-calculated value there. From there, the output will be coming out. Okay. Now, another factor which may affect here is you can pre-calculate the value and store it. Now, the larger the lookup table, which is used for storing this pre-calculated value, again, you will get better accuracy for this function. Okay. The smaller the memory which is used for storing this pre-calculated value, you are using less hardware, but again, the precision will be lesser. But again, in neural net, these kind of feed forward, they are mainly used for classification. So to some extent, the exact precision doesn't matter. Okay, so last time, if you remember, in the output layer, it is a softmax, right? Yeah, so this is like a classification. So let me give a simple example, which we'll be looking also using our MNIST classifier, which basically wants to find out whether the handwritten digit is 1 or 2 or 3 or whatever it is. So you will be giving the, I don't know, the handwritten digit to the input. You will be basically giving the pixel intensity values here. And basically, if this number is 1, this output should be high, and these remaining outputs should be low. You will have 10 classes here because number can be between 0 to 9, right? So whichever output is highest, we will say the input is representing that number. So if this output is, let's say, 0.8, and these outputs are say 0.1, 0.2, things like that, I will say like this is number 1. Now suppose instead of 0.8 here, in software it is coming 0.8, but in hardware it is coming like 0.7 here and maybe 0.15 here. No problem, still it will be classified as 1. These small loss in accuracy is acceptable in classification application. Okay, so. But again, beyond a certain point, the error will be too high and things won't work. Okay, so this also we need to keep in mind. Non-linear function, we will not implement directly in hardware. Instead, we will pre-calculate and implement it using lookup table. Linear function, we will do it directly in hardware itself, but we need to add a saturation logic to make sure the output is within the number, maximum number that we can represent using the bit width that we have chosen. Okay, now resource share. So previously told like we are going with hardware, because hardware is parallel and everything can be done parallelly in hardware, right? But we are taking a step back now. Maybe doing everything in parallel is not that good. Okay. Again, let me give an example. Suppose your neuron has 784 input. So when we go for this MNIST classification, the input neuron that will have 784 input, because I told, right, the inputs are representing handwritten digit, and that is a 28 by 28 pixel image. So there are totally 784 pixels. So basically neuron should have 784 input. Now what I should do inside the neuron, I need to multiply each of this pixel value with some weight value and add them together. Now if I do it in parallel, inside one neuron, I will need 784 multiplier. And I need some adder which adds the 784 multiplier output together. If you do that, there are two issues. One, again, if you take a typical FPGA and if it is using the DSP slices for multiplication, and if one neuron takes 784 multiplier, you cannot implement, say, more than 5 or 6 neurons inside one FPGA. And using that, you cannot make any neuron. That's a drawback. So we don't want to do that. We don't want to do 784 multiplication in parallel. What we may do is maybe we'll use one multiplier per neuron, and we will do only one multiplication at a time. So it may take 784 clocks to multiply all 784 input. Okay, so my latency is increasing, but the advantage is, yeah, I can make some real neuron. Otherwise, yeah, I cannot. That is one thing. Second one is, again, if you use an adder which can add 784 numbers in parallel and all, that will be a super huge combinational circuit. Your S-max will be impacted. Okay. So the frequency at which your circuit will run will be very low, which is a bad thing. Maybe to overcome that, you will add pipeline there. Again, resource utilization will go up. So not a good idea. So instead of that, what we'll do, we'll go for some resource sharing. So as I mentioned before, maybe we will put only one multiplier per neuron, And we will take one input, we will take one weight, we will multiply them, then take the next input, next weight, multiply it, so on and so forth. So some kind of resource sharing we'll do. Another practical issue, even if you implement 784 multipliers, assuming there are 784 input, you won't be able to give 784 input parallel. Okay, so how does the chip get the input? The input should either come from external world through some pins or within the chip using some interface, right? So if I am feeding the input from external world, I will need 784 pins to give this input parallelly. It is not practical. It is not feasible. Okay? It doesn't happen like that. If I am giving it through internal bus, I need to give 784. That means my bus width should be some 784 times whatever is the bus width, say 32 bit. I need a bus with this much width. And those kind of buses are practically not feasible because most of the buses within the chip, they'll be getting data from DDR memory. And DDR, it will not support these kind of bit width. Actually, it supports is like 512 bits. 512 bits. Okay. Here I need 784 input. Each input is like 32. So I cannot have it. So practically also, this doesn't make sense. So we do resource sharing. We will use, at least this I am talking from my perspective. I am giving up some latency here for saving some hardware. Okay. Okay, so finally we come to the architecture of the neuron. So basically, this is what I'm going to implement. So as I mentioned before, we will do training in software. We will get the weights and biases. So those weights I'll be storing in some kind of memory, some kind of RAM. So that memory I am going to call it as weight memory. But I am giving a provision here to update the memory later. Maybe a processor, he can update the memory later if he wishes, or at the design time itself, I can fill this memory with the weight values, which I got after tree. Same way bias, again, as I said before, bias is like one value per neuron that can be either kept as a constant at design time, or there can be a provision where the processor can update it later. Now, this is the interface through which the input is coming. Okay? So one input at a time. It doesn't matter how many inputs the neuron has, maybe 1 or 100 or 1,000 or 10,000, whatever it is. At one time, I'm going to accept only one input through this interface. I will take the corresponding weight from this memory for that input. Then I will use a single multiplier. Okay? I will multiply them together. I will give it to an adder, and the adder will be adding it with the previous result. That is how dot product happens, right? You input, you multiply with weight, you add it with previous result. At the beginning, it should be 0, but later, yeah, you keep on accumulating. So basically, this is a MAC operation, multiply accumulate operation. And finally, once all inputs are multiplied with the corresponding weight and added, we will add the bias also. That will, Akash, can you mute? Okay, so that output I am feeding to the actuation function. This can be either a lookup table based one or a circuit itself, as we have seen before, and the output will be going out. And we have a logic here for managing this whole thing, because as I mentioned before, when a new input comes, the corresponding weight should be taken from the memory. So there should be someone who does all these things. And like once all inputs are added, finally the bias should be added. So there should be someone who is doing all these things. That will be done by this interface and control logic. And that's it. So basically this is one neuron. single neuron. Now, once you have a single neuron, somehow you will make a neural network. There are practical challenges there I will discuss later. So assuming somehow you did that, you will have a complete neural net here. Now you need to use it somehow, right? So this is the architecture proposed for that. This can be again in any traditional FPGA, or for me, I mostly work with Zinc SoC platform. So in case of Zinc, I already have a PS here, processing system. If you're using other FPGAs, no problem. You can use a microblaze in case of Syed FPGA, or Neos 2 in case of a Intel FPGA. So we have a processor, we'll have a DDR. The assumption is after software training, either the values are directly stored in the weight memory at the hardware design time itself. If that is not done, those weights are stored in the DDR. Okay. And what the processor does, he will be reading those weights and biases, and he will be writing them to the neural net initially when the system starts up. If it is already done at the time of hardware design, yeah, that part can be skipped. Then we need the actual data for testing it. That data will be in the DDR. That's the assumption. Again, depending upon the application, that may vary. For example, if you are doing image processing, data can be coming from some camera. So somehow that data should be first stored in the DDR. That is possible. We have IP codes for that. So somehow that data will go to the memory. And there will be a DMA controller, which will be used for streaming that data from DDR to the neural network. We are not directly feeding it from the external world because the bit width and all might not match. Okay? So we cannot make any assumption like output from camera is these bits, things like that. So first of all, better to buffer it in the memory. Again, the process throughput speed might not also match. So better to buffer it in DDR. Then using a DMA, we stream it. Again, the processor is configuring the DMA control. So he will configure it, he will stream it to our neural net. And once the data is processed, this guy, he will give an interrupt to the processor saying like, okay, this input is processed. In that case, the processor will be reading from the neural net and getting the output, and he can do whatever he wants based on that. Okay, so this is the architecture I am aiming for. This is the architecture I am going to discuss. Okay, when I discuss, this will be on Zinc, and this will be PS. The DDR is already there. These things will be sitting in the PL part. And okay, so this presentation I will stop here. Next, I will quickly have a walkthrough to the code for the neuron. Before that, if you have any doubt, you can ask.
Vipin, there is one question in the chat.
Okay. In neural network models, there will be many zeros in each layer for weights. How do we exploit R? Yes. That as of now, I haven't specifically exploited it. What was the code? There is a layer, I forgot. In case of hardware design, the good thing is the tool will automatically remove those connections. You know, FPGA or generally hardware design tools, they are smart enough. And if they see a constant on some wire, all the circuits associated with that, he will optimize it away. Okay. That is from the tool perspective. That is one part. Other one, if we want to explicitly do it, yeah, we can explicitly do it by not having those connections here. Okay. Otherwise, also, even if it is, there are non-zero connections, sometimes drop of, what was the term? I forgot. There is a layer. dropout layer, right? Again, especially in CNN design and all, you will see like we'll be adding a parameter called dropout 0.25 or dropout 0.3. Even if some connections are non-zero, we will remove some connection. Okay, especially we'll choose the connections where the weight values are quite small. In software, they are doing it. Two reasons. One is to make the model simpler. Other one is avoid fitting. So that will avoid fitting them. Here also we can do the same thing. Yeah. So in case of hardware, if you do it, if it is non-zero, if it is zero, tool might be good. If it is non-zero, if I am doing a parallel multiplication, there is definite advantage. But in this resource sharing architecture, whether there will be any real advantage, I don't think so. Because anyway, I will have to use one multiplier per neuron. So number of multiplier, it won't reduce. Latency also, it won't reduce. So hardware, I will have to see how to exploit it. As of now, I am not doing anything explicitly. Okay. But usually this is done to avoid OR fitting actually. Some connections are removed to avoid OR fitting. Okay. Anything else? Okay. If nothing, I will quickly show the code for Neuron, how it might look like. Okay. I hope you can still see my screen, right? Can you see?
Yes, sir.
Yes,
okay.
Vipin.
Yeah, so this is the neuron model that I have discussed. All the code is freely available. I will give you the link also towards the end. So this is basically this guy actually. So here you can see everything is parameterized, okay, because later we will see there is an automation platform on top of it where it will be configuring all these parameters. That is also Python based that we will discuss in the next session. But basically, always parameterize everything, whichever you can do parameterize. So basically, yeah, so this is the input which is coming from the external world. So basically there is a valid signal. So these one, weight valid, bias valid, weight value, bias value, these are optional. As I said before, if the weights and biases are not configured at design time, if the processor is going to configure it, there should be some interface for doing that. So this interface is used for that. Okay. So the processor will give me the weight and he will make this weight valid high. So you'll see like almost all my design, I'll be following ECE IIIT or ECE stream based interface. Mostly I'm targeting Chinese FPGAs because that's their standard interface for all the IP cores. Okay, so this whole thing is optional. This is for configuring weights and biases from the processor. If everything is done at design time itself, yeah, this will be just redundant. And this is just the output of the neuron. And this is basically saying the output from neuron is valid. Okay, so I'm just going through the main part. I'm not going through everything. So this logic is basically used for storing the weight values into the memory. Okay, so here you can see there is something called this weight memory. That is this guy storing the weights. So the code that I showed before, that is used for storing the weights inside the memory from the processor. Now there is an option whether that weights should be stored from the processor or at the design time itself, we fill the memory with those weight values, right? If it is pre-trained, we already know the weight values, so we can directly fill it. at the design time itself. So that option is there. So basically, this is the memory. I'm not using any Xilinx IP course directly, so that it can be implemented on any FPGA or ASIC also, no problem. So this is the memory for storing it, Verilog 2-dimensional one. And here you can see, so this parameter basically decides whether the memory should be filled at design time itself, or whether it should be filled at runtime from the processor. I'm using for this example, I'm using a pre-trained one. That means all weight values are available after software training. And all these parameters, this tick define, they are stored in this file. So there you will see the first thing itself is like pre-trained, using a pre-trained model. So he will see it. So what he will do, he will fill this memory with the pre-trained weight values. So the pre-trained weight values will be coming from something called as a weight file, and each neuron will have a unique weight file. Okay, so how to generate it, again, I will show in the afternoon. So it will look something like this. Okay, so this is using 16-bit fixed-point representation for the weights. So here you will see like there are 1,000 entries, because I am telling in this file include.p, I'm saying basically my first layer, the neurons in my first layer, it has 1,000 input. And there are 1,000 neurons. Okay, in the first layer, sorry, not 1,000, 10. In the first layer, there are 10 neurons. Where? Okay, so here there are 10 neurons. Each neuron has 1,000 input. That is what is based here. Same way for other layers also, you can see. Second layer, there are 5 neurons. Each neuron has 10 input, 2 neurons, 5 input, so on and so forth. And what is the activation function used by each neuron in each layer? That's also defined here. So since I said like it is a pre-trained, he'll be reading it from the weight file, and each neuron will have a separate weight file. And the for name of the weight file, again, I have used the special style. That will be W underscore. This 1 is representing which layer, and 0 is representing the neuron number. So this is basically saying this is the weight file for the 0th neuron in the first layer. Okay, and he has 1,000 input. That means he should need 1,000 weights. So these are those weights. So at design time itself, Vivado, he will read this file and he will directly initialize the memory with those values. Now, yeah, so this is like a normal RAM coding, you know. Only additional thing is, yeah, there is an option for initialization or runtime memory. So that's about weight, and yeah, so this is basically filling the weight if processor is filling it, otherwise no need to do it. Same way, bias value, since there is only one value for bias, I have a single register for storing it, this bias register. Again, if it is pre-trained, that is directly read from a file at design time. If it is not pre-trained, the processor can write to it. So bias also looks similar, like this one. Again, same conversion, B for bias, 1 for layer number, 0 for neuron number. This is the bias value. Again, I got from the software training, but represented using fixed point representation. Okay. Then, okay, where is the main thing? Okay. Weight memory. Okay, so here, this one. This is my actuation function generation block. Again, I have two options. As of now, two things are supported. If actuation type is Sigmoid, it is using a ROM with the pre-calculated Sigmoid values. If it is not Sigmoid, currently only ReLU is supported. So there are only two choices. I can add hyperbolic tangent also, I just have to calculate the values and put it in the memory. But the idea is similar. So this is the sigmoid memory. This is the ReLU. Now generate, you might be knowing in Verilog, generate will enable you to selectively instantiate module. Okay. So if actuation type is sigmoid, it will instantiate this one. If it is not sigmoid, it will instantiate this one. So sigmoid, if you see, this is the sigmoid memory. What it does, like similar to weight memory, I have pre-calculated the sigmoid value and it is just reading it from there. So you'll see like sig content. This MIF stands for memory initialization file. That is highly specific. Okay. The extension should be MIF and each location represents the data at each location in a memory. So this is the content of the sigmoid memory. Again, you will see like there are 1024 entries because I have the control that what should be the size of the sigmoid memory. So here you will see like sigmoid size 10. That means 2 to the power of 10. Those many depth will be there for the sigmoid. So I can put different values here. Based on that, he will automatically generate sigmoid memories with different sizes. As I mentioned before, larger the number there, more accuracy, but more hardware. Yeah. ReLU is very straightforward. Okay, so ReLU is basically this one. It is just a signed operation. If it is positive, output is same as input. If it is negative, output is 0. But as I said before, you cannot blindly make output same as input because hardware will have to check for overflow. And if there is an overflow, we'll have to do a saturation. Okay, so that is basically done here. So how overflow is checked and run? Yeah, you can check the logic here. Otherwise, I have like a 4-hour long video, detailed video discussing each line in the design. I will share with you, and you can have a look there how it is done, whether overflow is happening or not. So basically, that is the thing here. Now, what is happening? Yeah, so this is our multiply guy. Although last time I said like signed multiplication is not that great. I'm actually using signed multiplication here to reduce the amount of code. So you can see basically what is happening here. I'm multiplying my input, which is coming from the external world, with the output from the weight memory. Okay, so when I get a new input, the output from the weight memory will change because this circuit, this is the one who is reading from that weight memory. So here you can see, whenever my input data is valid, that means I have a new data coming from the external world. I am incrementing the read address from that weight memory. Okay, so as I get new and new data, I'll be reading newer and newer weight values. So I will read them and I will multiply them, that I will get here, and that I am adding. So all these if, else if conditions that you are seeing here, that is for preventing overflow. Okay, so basically, again, details I will share later. Basically, this is the idea used for overflow. When you are adding two positive numbers, if the result is negative, that means there is an overflow. Same for negative also. Okay. That is how we find out whether there is an overflow. If there is an overflow or underflow, both can happen. This will basically do a saturation. It will do saturation. So we will sum add. So I have to. And you can see that sum is actually going as the input of sigmoid. So basically the sum of that multiplication addition, that is going to the input of the activation function, whether sigmoid or ReLU. So there will be always output coming from sigmoid or renu, but I have a control signal here, which will make sure only after all the inputs are processed, the output value from the neuron will become high. Only when the signal is high, that tells that the output from the neuron is valid. So how that signal is generated, you can see here, is sigmoid valid. Weight -1 and input data value. So what this basically says, num weight is number of weights, which will be same as number of input. Okay, read address equal to num weight. That means I have read all the weight values. That means I have received all the input values. Once I have received all the input values, then only I am making this out valid high. You will see some additional signals here. That is for managing the pipeline, because this thing is completely pipeline for better timing performance. So here I am checking whether I got the input, but after getting input, I will take 3-4 additional clock, because that input should go through the multiplier, which is one level of pipeline, then the adder, another level of pipeline, then actuation, another level of pipeline. So there will be a latency of 4 clock. That's why there is another guy checking, like, after getting this input, whether 4 clocks have elapsed. If 4 clocks have elapsed, that means my neuron has completely processed that particular input. Then only this output will become high. Basically telling, yeah, neuron has processed it. Okay, so this is the main idea. So I just want to correlate between this figure and the code. So everything that you see in the figure, that is actually here. Detailed code review, I will share the video where each line is discussed, how it came like that. Okay, so I think morning session, I will stop here. If you have questions, I will take now. Because how the remaining layers are designed, I will discuss in the later session. Okay, if you have something to ask, you can ask.